Well, thank you so much, Martin. It's certainly an honor for me to give a talk here at the Royal Institution. I'm well aware of the many fantastic lectures that you've had here going back to Faraday in 1856, so it's an honor for me to be here. I thank Martin very much for his introduction. I can say that working with Martin has been one of the great privileges of my life, and so it's a particular pleasure for me that he's able to be here today. And as you'll see, Martin plays an important role in the story I'm going to tell tonight. It's a story about the Cold War. It's a story about a high school science project. And it's a story about how a generation of astronomers, both theoreticians and observers, together finally won a hard-won understanding of how the galaxies in the universe are arranged, what the architecture of the universe is. And this story starts with Edwin Hubble. And this is a picture of the Rosette Nebula. This is a gas cloud in our own galaxy. It's 5,000 light years away. So light's been coming to us at 300,000 kilometers a second for 5,000 years. It's forming stars here in the middle. I put the eclipsed moon here in the foreground. It doesn't go anywhere near this, but I just put this in the foreground to show you the angular scale of this. And you say, why didn't I notice this thing in the sky? It's bigger than the moon. Well, it's very, very faint is the answer. Okay. Next. Oh, well, go. This is another nebula. This is the Andromeda Nebula. It's also bigger than the moon in the sky. You can see this with your naked eye, just the central brightest portions on a really dark night. Many people thought this might be just another gas cloud in our galaxy. But Hubble found very faint variable stars of a known type, Cepheid variables in this galaxy, which proved that it was very, very far away, much further away, so that it was outside of our own galaxy. And in fact, given its angular size and the distance of it, it was actually similar in size to our own galaxy. So this was no little gas cloud. This was an entire galaxy of hundreds of billions of stars, just like our own. And it has two satellite galaxies as well. So this opened our eyes to the world of galaxies. And there was, of course, other spiral nebula like this that were smaller in angular size that must be further and further away. So Hubble started measuring them. This is our best picture to date, taken with the Hubble Space Telescope, named after him. And this is the Hubble Ultra Deep Field. And I've, again, superimposed the moon and Mars and Saturn in front of here so you can show what a tiny region of the sky we're looking at here. And this whole ultra-deep field has about 10,000 galaxies in it. Everything you see in here is a galaxy. And the little faint ones, the tiny ones here, these are about 13 billion light years away. And so if you multiply the area of the sky that we're seeing here to cover the whole sky, you can see that within the range of the Hubble Space Telescope are about 130 billion other galaxies. And the question is, well, how are those galaxies arranged? Now, Hubble was not finished. He discovered something else. He discovered that the further away galaxies were, the faster they were moving away from us. And you can tell the velocity of a galaxy by looking at the Doppler shift of its spectral lines. If it's moving away, those lines are going to be red-shifted. You can measure that, and you can determine the velocity. So he found that the redshifts of these galaxies were getting larger and larger as he was going further and further away. And in fact, he and Humason in 1931 found galaxies moving away from us at 20,000 kilometers a second, which is an extraordinarily high speed. This is a uniform expansion. It's like raisin bread baking in the oven. As the bread gets bigger, the raisins move further apart. And a more distant raisin from your raisin is going to be moving away from you faster because there's more bread in between the two of you. So this is a linear, homogeneous expansion that Hubble has discovered. And it's this figure in 1931 that convinced Einstein that the universe was really expanding. Now, there was a ready explanation for this at the time. In 1922, Friedmann had published a exact solution of Einstein's equations of general relativity, his theory of curved spacetime to explain gravity. And this was a universe model that looked like a football, and it started with a Big Bang at the bottom, and then we're plotting one dimension of time this way, and space is one dimension around the circumference of this. And the only thing that's real here is the pigskin itself. Forget the outside, forget the inside. This is a curved surface, and the galaxy world lines are going to follow the seams in the football. They're going as straight as they can in this curved surface, and their mass is causing the curvature in the football shape, and it's causing them to slow down and eventually collapse at the big crunch. You do not want to be around at the big crunch. But we'd be living here in this model where the universe is expanding. And so this is because the space is stretching. It's not expanding into anything, but it's just getting bigger. George Gamow in 1948 pointed out that if you extrapolated this back to the past, the universe would become very dense and very hot. And this hot radiation should still be bouncing around in the universe today. And he and his students, Herman and Alpher, said that you should still be able to see it today. And this, in fact, was discovered by Penzias and Wilson in 1965, and it proved that the universe started with an early hot Big Bang. And I worked for Penzias and Wilson as a graduate student, and I got to run the telescope that detected this background radiation and found its temperature to be 2.7 degrees. And so I would run the telescope at night by myself, and I would occasionally go and look at the moon, and I could see the thermal radiation coming from the moon. I could measure the temperature of the moon. So this discovery of the microwave background radiation really proved that we started with a hot Big Bang model. Now, how were the galaxies arranged in space? Well, people knew that they were in clusters. And here's Fritz Zwicky. I knew him at Caltech. He's probably the premier investigator of clusters of galaxies. And this is his catalog of clusters of galaxies. He was quite a character, as maybe you've guessed. And I would tell you that when the colloquium speakers came to Caltech, there were two people in the audience they feared. One was Richard Feynman, and the other was Fritz Zwicky. Feynman might raise his hand at the end of the talk and say, oh, but that violates energy conservation, doesn't it? And Zwicky might raise his hand and say, I did this already in a paper in 1934, and here's the reference. And you'd go look up that paper, and he did. He wrote a paper on that in 1934. So Zwicky studied the Coma cluster. This is every point. This is Zwicky's own drawing. This is every point in here is a galaxy. It's a centrally condensed, relaxed cluster of galaxies. It looks rather like a globular cluster of stars. This whole cluster is moving away from us at several thousand kilometers a second, part of the expansion of the universe. But there are differences in velocities between galaxies here due to Zwicky measured by the Doppler shift, that show you their orbital motions around the center of mass of the cluster. And from this, he could determine the mass of the cluster. And he found, to his surprise, that it was several times larger than the mass that could be accounted for by the galaxies. So he called this extra mass dark matter, And we know today that this dark matter must be made of not ordinary materials. Ordinary matter is made of protons, neutrons, and electrons, and this has to be made of something else. Some new form of elementary particle that we haven't yet detected, and we know it's there because we can see it in the mass of the cluster of galaxies, and we can also detect it by its gravitational lensing properties of background galaxies. And you know, Zwicky wrote a paper on that in 1937. So we know that dark matter is there, and Zwicky discovered that in 1933. So here is a cluster of galaxies. This is a picture from the Sloan Digital Sky Survey, the Perseus Cluster of galaxies. So we know galaxies are in clusters. This is a picture. How do they form? This is actually a picture from Martin's and my paper, 1975, and it's in the book. And this is what's going on. You have a slight density perturbation in the early universe, a tiny fluctuation, and there's excess density. Because of that excess density in the fluctuation, it's going to be more gravitational attraction than an average in the universe, so it's going to decelerate more than the whole universe does. That would be out here. So it's going to start expanding slower than they do, and therefore it's going to get denser still than the rest of the universe. Eventually it's going to turn around, stop expanding, collapse back down, and relax and form a cluster. And then later stuff will fall in and make the envelope. This is time going up this way and space this way. And then at very late times, even at the present day, you may see something falling in now. And this is exactly what Andromeda is doing. We live in a local group, a small cluster, and Andromeda has been decelerated by our galaxy, and the two of them are falling back together. So this is coming back here. So galaxy clusters can form from small fluctuations in the early universe. And the American School of Cosmology, led by Jim Peoples, said this is what's happening. Clusters are forming. First, galaxies form by the same mechanism. A fluctuation forms, decelerates, collapses, and then galaxies will cluster into clusters, and then clusters themselves will cluster into superclusters. So you have this hierarchical pattern of clustering. And so this is like meatballs in a low-density soup. And then these just act like vacuum cleaners, drawing additional material in. So you get this meatball soup picture of how the galaxies are clustered. And this was the picture that the American school was entertaining. Meanwhile, over in the Soviet Union, Zeldovich and his colleagues were spinning a completely different picture. Zeldovich said, okay, well, if you had a perfectly spherical region, that could collapse and form a cluster, but suppose it was irregular. Suppose it was a flattened, sort of a flattened sphere here. How would it collapse? It would collapse into a pancake first. And he believed that as the gas collapsed into a pancake, the density would go way up, and as it dissipated energy, you could trigger galaxy formation. So he believed that galaxies were formed in pancakes, that you formed the structures first, and then the galaxies in the pancake. And so how would the pancakes be arranged in space geometrically? Well, they would form a giant honeycomb pattern here. There'd be big empty voids here. And in fact, Bob Kirshner and his colleagues had found were finding a big empty void in the constellation Boötes. So Zeldovich believed that galaxies formed on these pancakes. There'd be denser filaments in the edges, and then the clusters would be at the corners of these, where several of these plates came together. And so this was the picture that the Soviet school had. Now, why did two schools develop? Okay, well, even with modern communications, the sometimes you just have to travel and pour your ideas right into the other person's ear to convince them. And so Zeldovich was not able to travel outside the Soviet Union because he'd worked on the nuclear program there. And Soviet scientists in general did not get to travel outside the Soviet Union. So you developed these two schools. Now, however, Martin Rees did travel back and forth. He was sort of like Marco Polo to me. And so when he invited me to come over to Cambridge University as a postdoc, he told me excitedly all the things that the Russian School of Cosmology were coming up with. And in our paper, we tried to marry some of those best ideas from the Russian school and the American school together. That's what we were trying to do. So this is the opposing school. Now in 1983, Zeldovich and Shandarin and Einasto wrote this important paper. Let me go back and show you this. If you take a slice of this universe, you expect it to show a cellular structure, okay? And let me mention that, of course, this is in a way exactly the opposite of the American school. In this picture, the high-density regions where the galaxies live, you'll notice, are all in one connected piece, the honeycomb. But the voids now are the ones that are isolated from each other. So there's one high-density region and many isolated low-density regions. So it's the exact opposite of the American view. So here's two slices that Einasto made. This is observational data. Here's clusters of galaxies here. And you can see the cells here. And so when people looked at this was a big support for this picture. And Zeldovich also noted that our own Virgo supercluster nearby seemed to have a sort of pancake geometry. So this was the picture from the Russian school. Now, at this time, a new theory came along. This was, Guth proposed the theory of inflation, and he proposed that instead of starting off with a singularity at the beginning of the universe that was the Big Bang, he wanted to start it off with a brief period of accelerated expansion, which he called inflation. And this gave you a little extra time in here for different regions to get in causal contact with each other over what the Big Bang could offer. And when the universe was tiny, so different regions could communicate with each other. And this helped to explain the uniformity of the temperature of the microwave background we see when we look in different directions, something the Big Bang wasn't able to do in a natural way. So this period of acceleration, this could start with a very small circumference here, maybe 10 to the minus 27 centimeters, and then it had this very rapid accelerated expansion. This was powered by something we call a high degree of vacuum energy. Well, what's vacuum energy? A vacuum is when we take first all the people out of the room, then we take all the air out, then we take all the light beams going through the room out. We just have totally empty space here. You would figure that would have a zero density. But we've discovered now the Higgs particle, which is associated with the Higgs field, and the Higgs field permeates all of space. It's what gives particles their mass. And the Higgs field is capable of producing a non-zero vacuum energy, as well as other fields are capable of producing vacuum energy. We sometimes call this dark energy today. So the vacuum itself might have a non-zero positive energy density. Now, in special relativity, one of the properties you wanted for the vacuum was that it had no unique standard of rest. So if you had two rocket ships going through this vacuum state at different speeds, it would be nice if the rocket ships measured equal energy densities, so you couldn't tell the difference. You couldn't tell anything about whether you were at rest or moving or not. So, but if that's true, by the logic of special relativity, the only way that that would be possible for rockets moving at different speeds to measure the same amount of energy density would be if the energy density was accompanied by a negative pressure of the same magnitude, but opposite in sign. Now, this negative pressure is sort of like a universal suction, but it's uniform, so it produces no hydrodynamic effects. As you know, it takes pressure differences to make the wind blow and knock you over. So we have in this room 15 pounds per square inch of air pressure, but we don't notice it because it's uniform. And so it has no hydrodynamic effects, but according to Einstein's equations, pressure has a gravitational effect as well as energy density. And so it's a negative pressure, so it has a negative or repulsive gravitational effect. And it operates in 3 dimensions, 2 horizontal dimensions, front, back, left, right, and the vertical dimension, up, down. So the pressure is operating in 3 dimensions. The energy density, therefore, is the repulsive effect of the negative pressure, the gravitational repulsive effect of the negative pressure, is 3 times as potent as the gravitational attractive effect of the energy density. So the overall effect of this dark energy is repulsive, and it causes the universe to start to expand. So even if you started it statically, it would start to expand. And it doubles and doubles and doubles in size once every 10 to the minus 38 seconds or so. So you know how that goes. 1, 2, 4, 8, 16, 32, 64, 128, 512, 1024. If I did that again, we'd be up to 1 million. So the universe expands by an extremely large factor in a very short period of time. This can explain why the universe is so big. It's one of the attractions of the inflation theory. So inflation was a theory that could explain lots of things. And we believe in inflation because it explains very well the fluctuations that we see in the cosmic microwave background. And we also believe in inflation because we can see a low-grade inflation starting to occur at the present epoch. 2 teams of astronomers discovered that the expansion of the universe is accelerating today. And it's accelerating such that it's doubling in size. It was going to be doubling in size about once every 12.2 billion years. So this is a very low-grade inflation. There's a very low amount of vacuum energy. And in fact, it's corresponds to about 7 times 10 to the minus 30 grams per cubic centimeter. It's tiny, but it's enough to have this dynamical effect and that we can measure. And they won the Nobel Prize in physics for this. So we see a low-grade form of inflation going on right now. Now I realized that the theory of inflation, one of the other nice things that it has is that things are so small. First, let me mention a problem that Guth had to solve. Guth wanted the inflation to end right here uniformly and then turn that energy into thermal particles to start a hot Big Bang. So what he wanted to have happen here was like you have this inflating sea, high-density inflating sea. It's like you'd like to put the pot on the stove and have it turn to steam all at once. It's the whole pot turned to steam. And that would make our Big Bang uniform universe that we saw. But he knew that what would happen instead was just what happens when you put your pot on the stove, that you will form bubbles of steam in the expanding sea. So it would form bubbles of steam and a uniform high-density sea. This was a highly non-uniform distribution, not what we thought the universe would look like. So that was a problem that needed to be solved in inflation. And so I wrote a paper in 1982 saying that the solution to this problem was that we lived in one of the bubbles. And if our whole universe were a bubble universe that we lived in, then seen from inside one of the bubbles, remember you're looking back in time, you're just seeing the uniform inflating sea that occurred before that. From inside one of the bubbles, your view was uniform. And so this would solve Guth's problem. Very shortly after my paper appeared, there was a paper by Linde, and an independent paper by Linde, and another independent paper by Albrecht and Steinhardt, proposing basically the same thing. And they had a detailed particle physics scenarios that could make this work, and this was called new inflation, and it solved a Guth's problem. So let me show you this. This is a space-time picture of how this would work. Time is going this way. You start with a tiny inflating region here. It's an inflating sea, and then bubbles are forming in this. These are bubble universes, and then the galaxy world lines are going to fan out here. These bubbles are going to expand forever, and the whole thing is going to keep expanding forever. And we're living in one of these bubble universes, and the space between us and other bubble universes stretching so fast that the light from them is not getting over to us. So this is a picture that we have of what we now call the multiverse. And so while we can't see these other bubble universes, it seems that we've got a lot of evidence in favor of inflation, and it seems like almost an inevitable consequence of inflation that you would form a multiverse at the end. So this could go on forever, and you create an infinite number of these bubble universes. Now, I realized that one of the nice things that inflation did for you was that it started off so small and so rapidly expanding that the uncertainty principle told you that you would have random quantum fluctuations. And these could start the fluctuations that were going to eventually grow up into clusters of galaxies by the present day. So inflation predicted, though, that these were random quantum fluctuations. That meant that you just put random uncorrelated waves through the universe, and you could put these on your computer with a random number generator. And here's the thing, if you had a series, just imagine sine waves going every which way, uncorrelated with each other, at different wavelengths and things. And the thing that was true about this was that if you had a positive fluctuation over here and a negative fluctuation over here, this would be above average in density, this would be below average in density. If you simply flipped the sign of your random number generator at the beginning that you told the computer to use, it would switch all the negative density fluctuations from positive density ones. And so it would just reverse the two regions. This part would now be the high density part, and that part would be below average density. So one thing that must be true with random fluctuations, which inflation predicted, was that the initial conditions, the regions that were above average in density and the regions that below average in density had to be geometrically similar, had to be geometrically interchangeable with each other. This was not true in the American model, where you had isolated clusters and one low-density part. It was not true in the Russian model, where you had one high-density part and many isolated low-density parts. They were, both cases, geometrically dissimilar. Well, I knew there was a third way, a sponge-like topology, because I had done a high school science project. Now, here are the 5 regular polyhedrons. These have been known since the time of the ancient Greeks, and they're the only ones that you can have that are regular faces and all the vertices look the same. So here's one. Here's the cube. It's you'll notice that it's 3 squares arranged around a point. You can think of this as a surface made of squares. I mean, I don't have anything inside here. This is just made out of squares. So there's a 90-degree angle here, and here, where the top and the two sides meet. So you got three 90-degree angles. So the angles around this point are 270 degrees. That's less than the 360 degrees you expect in a plane. So all of these polyhedrons have less than 360-degree angle around a vertex. Here's another one. This is an octahedron. It has 4 triangles around a point. So that's 4 times 60 degrees. That's also less than 360 degrees. So this is a property that all of these have, and this is the only way you can do it. 3 triangles around a point, 4, 5 triangles around a point, and 3 pentagons around the point. Those are the only possibilities. But Mr. Kepler, the man who invented the laws of planetary motion, which are so helpful to Newton, he thought that you could also count as regular polyhedrons the well-known 3 regular planar networks. These were surfaces, regular surfaces made of polygons. They were just as good as a polyhedron. They just had an infinite number of faces. Okay? So here's the checkerboard. It has 4 squares around a point. That is 360 degrees. Here is the 6 triangles around the point. That's 360 degrees. And here's 3 hexagons around the point. That's 360 degrees. So if you broaden your definition of a regular polyhedron, you could get this. 3 additional regular polygon networks. Now, this is an illustration from my high school science project I submitted to the Westinghouse Science Talent Search. The Science Talent Search still goes on today. It's run by Regeneron. It's had several sponsors over the years, but then it was sponsored by Westinghouse. It was one of the most prestigious science contests for high school students in the United States. And my project was on relating space-filling packings of polyhedrons. This is a semi-regular polyhedron. It's a truncated octahedron. You just cut the corners off the octahedron, and it has square faces here, and it has hexagons here, 2 different kinds of faces. This is a truncated octahedral box, and you stack them here, and you get this space-filling, body-centered cubic pattern. You could fill up a whole warehouse of these. And so my project was on relating these stackings of polyhedrons to the different crystal structures. In this case, metallic crystals, and this was like the metallic crystal structure you got for sodium. So that was my science project for the Westinghouse, and it went on to win the 2nd place in that contest that year. And Glenn Seaborg was one of my judges, and he was, of course, has an element named after him, Seaborgium, as well as winning the Nobel Prize. So this was quite exciting for me. Many years later, I was asked to be the chair of the judges for this contest, and so I served in that capacity for 14 years. And I think the best science project I saw during my 14 years in that contest was by Jacob Lurie. It was a math project. It was the #1 winner that year. And this was on surreal numbers. It was a really amazing project. And he went on to quite recently win the $3 million breakthrough prize in mathematics. The most famous person to go through the contest in my years is no doubt Natalie Portman. She was one of the 300 semifinalists in the contest that year. And it was my job as chair of the judges to take a ranked list of the 300 best projects that have been selected as semifinalists by a team of evaluators, and to winnow that list down to 120 to go on to the next stage of judging. And I actually remember her project because I really, really liked it. It was a project about how you might get an enzyme to digest waste paper and produce hydrogen fuel. So it had this environmental thing going on. And I really liked it, and I put it enthusiastically into the top 120 pile. So she's known for being in one of the 300 semifinalists, but actually she did 2.5 times better than that. And when they published her paper on the internet, I had no idea she was an actress. I remember it was a woman's project from New York, but I had no idea that she was an actress or who she was. So it was judged entirely on its scientific merits. And later, her paper was published on the internet, and I recognized it immediately as this project that I had actually particularly liked. So instead of winning a Nobel Prize, she won an Oscar. So she turned out all right. So it was a thrill for me to work with all these fantastic students during the years. And I think contests like this are very important because they encourage people to try scientific research early in their careers, see if they like it. Now, I won the second place scholarship, and this paid for half of my Harvard education. But the most important thing to happen was something I noticed when I looked at the plastic model of this that I was building. I had made a lot of plexiglass hexagons, and I was gluing them together. And I noticed that there was a butterfly pattern of 4 hexagons that came together around a point, which you can see there. And I've replicated this here today. This is what they looked like. And I've got 4 hexagons around a point. How can you do that? Well, it's a saddle-shaped surface. This is a negatively curved surface in mathematics. And these are positively curved surfaces like the sphere, and the plane is in between. So these have more than 360 degrees around a point. And not only that, was there this one configuration, but it could be continued. And in fact, I noticed that if I just took all my squares and threw them away, the boxes would all open up, and I would have one continuous sponge-like pattern of hexagons that was all related and that divided space into 2 equal parts. And so this was a new, different polyhedron that had more than 360 degrees around the point. This is my high school science project for that, which I entered in the National Science Fair International at the time. This is now the International Science and Engineering Fair. You can enter that from Britain and countries around the world. And I made models of these polyhedrons that I had found. And here's a close-up of them. Here's squares, 6 around a point. Here's pentagons, 5 around a point. These are ones that I had found. And when I got to Harvard, I submitted this to the American Mathematical Monthly. And the referee pointed out that 3 of these had been discovered by Petrie and Coxeter in 1926. But these 4 were new, so it was publishable. And since my paper came out, a crystallographer named Wells has discovered 3 more of these. So these are sponge-like networks. Well, now, years and years later, when I was confronting this problem in astronomy, I knew that there was something that would divide space into 2 equal parts, a sponge. So here's a picture of that square 6 around a point, and it divides space into, it could be a high-density part here and a low-density part here that are interlocking. And so if you have a marine sponge, here's your marine sponge, it has water passages going through it, bringing nutriments to all the insides of the sponge. And if you poured concrete in those passages, that could solidify. And then if you took acid and you dissolved away the poor sponge, then that would be gone, and you'd be left with a concrete sponge. So that also would have air passages going through it. So the insides and the outsides of a sponge can be the same. And so this is just what the initial conditions in inflation should look like, interlocking sponge-like topology. So I got together with Malott, who was an N-body simulator, and Dickinson, who was an observer, and we wrote a paper called The Sponge-like Topology of Large-Scale Structure. And Malott made a simulation. This is initial conditions based on inflationary initial conditions. So these are slight density fluctuations here, ever so slightly above average, and the above average regions of these random initial conditions look like a sponge. You can see the holes here, and you can see that it's all in one piece. And here's the other half of this cube. This is the low density parts, and these are also a sponge. You can see the holes over here, and this is all in one piece as well. So that was our initial conditions. Then we evolved it on the computer up to the present epoch. And then we're going to smooth this data because we don't care that the galaxies are individual points. We want a census of galaxies like you take. I want to know how the population goes on the scale of counties, so you'd count here. So we smooth the data on a distance of 24 million light years. And then we counted the density of galaxies. And so this is how the regions look today. The contrast has been greatly enhanced, but you'll notice that we took the median density contour that would divide space into two equal volumes. And you'll notice that the high density parts here are exactly where the high density parts were in the initial conditions. They've just grown up and become higher and higher density. And the low density parts also are mimicking what they had in the initial conditions. Small scale fluctuations will grow in place, becoming bigger and bigger without moving in the standard picture. So we discovered that if you looked at the universe today and you smoothed it, you could get, this is also smooth with the same smoothing length, you could get a picture of what the initial conditions look like and see whether they resembled a sponge, which inflation would predict. So here's an observational sample that we looked at, a tiny one, and here's the Earth here. Here's the Virgo supercluster up here, and the high-density region is all in one piece. And here's the low-density region. It's all in one piece here. And this is, you can see a hole over here. We measured it. These have sponge-like topology. This is what a honeycomb would look like. We smoothed the data. We looked at one of these Zeldovich honeycombs, and the high density region is all in one piece. This looks exactly like Swiss cheese. We call this a Swiss cheese universe. It's equivalent to a honeycomb. And the isolated voids, if you look at the low density half of this picture, you can see them. They look like, you can see them there separated from each other as high density isolated regions with positive curvature on them, on those surfaces. So this is looking quite different, for example, as to what we're actually seeing in even that first observational sample. So here I am with David Weinberg, who worked on this project. There I am, I worked on time travel. It's a little time travel to the past for me. So this is how I looked then. And we're looking at some of this data. And we used the stereo glasses, we made red-blue stereo pictures, so we look like we're looking at some old science fiction movie. And about this time, deLapparent, Geller, and Hooker produced this picture. This is a slice picture of the universe. It has the Earth here. You're looking at a narrow slice. They're measuring distances out here by using the Doppler shifts of the galaxies and Hubble's expansion law. And this is a complete sample, so there's no question about you missing any galaxies. And they found these incredible structures. You can see cells here. And this looked quite like the Einasto picture, only more spectacular. And many people looked at this picture and said, this is like the honeycomb picture. And in fact, Geller and Hooker described this as a froth of bubbles, which is geometrically equivalent to a honeycomb, isolated bubbles with the walls all connected. So this picture looked like it favored the picture of the Russian school. Now, they kept taking data, and they made a thicker slice, put together 3 slices here, and one of these filaments here became more prominent. They called this the Great Wall because it reminded them of the Great Wall of China. And this was about 750 million light years long. It was an extraordinary large structure. Now, Park and I did a simulation. This is Park's thesis. He did the simulation. I told him to make the simulation. So what he did was to make a simulation that had 4 million particles in it to simulate for the first time a region as large as this observational sample by Geller and Huckra. And so this was made using People's new idea of what's called cold dark matter. So Peoples proposed that the dark matter of Zwicky was made up of weakly interacting massive particles, and that the nice thing that, and also Blumenthal, Pagels, and Premack produced the same idea around the same time independently. And the wonderful thing that this did for you was that the normal matter was coupled to the hot thermal radiation, because in early days the atoms were ionized and we had positive and negatively charged particles. So they were stuck to the radiation, which had a pressure which resisted collapse. But the cold dark matter could start growing earlier than the matter could, and this helped you, particularly at small scales, this helped to be able to make galaxies early. And so it helped people to make the galaxies first, which he wanted to do. And this was quite a breakthrough, and Park's simulation is based on the cold dark matter model of Jim Peoples. And when we first looked at this cube that he made, and there was a giant filament in it, and so he just made a slice of that. And the agreement, this just looks extraordinarily like the stuff that Geller and Hooker were seeing, and these long filament like this. It proved that cold dark matter could make structures as big as this, and it also proved that it could make things that looked like this. But we knew for a fact that this simulation had a sponge-like topology because we could see it in 3D. So we knew that the simulation with a sponge-like topology could look like the Geller and Hooker sample. Meanwhile, but we had to wait until they got a complete 3D sample of that. Meanwhile, we were looking at other 3D samples that were complete. This is a Giovanelli Haynes observations. This is the high-density half. This is the low-density half of their survey. This is the Perseus cluster in here, which I showed you. This is the Perseus Pisces supercluster, which is a giant filament of galaxies. And you can see the hole here. The high-density part is all in one piece. This is the complementary low-density part. And you can see the holes here, and you can see that this is all in one connected piece. So this is a sponge-like topology, Giovanelli and Haynes. Now, later, when the Geller and Hooker had completed their 3D survey by adding more and more slices, this is their final results. The Earth is here. This is the northern hemisphere. This is the Great Wall in here. This is the southern hemisphere, which they added to their survey. And here you can see that the Great Wall is actually a filament connecting clusters of galaxies, and you can swim from this void around into that void. And so this is a sponge-like topology. In a sponge-like topology, the great clusters of galaxies are connected to filaments, by filaments, to make one connected piece. That's the high-density part of the sponge. And then the voids are connected by tunnels to form the complementary piece. So this is indeed a sponge-like topology. You look at it over here, we've smoothed it at a larger scale, a lower resolution version, and you can clearly see here that the Great Wall is a filament connecting clusters of galaxies, and there's a hole in the distribution here. I want to look in closely at this part of the survey. We're going to turn it upside down, and here it is. And Michael Vogeli, who's working on this, this is the Earth here. There's a big void in here, and he put a light in this here, and you can see the red light shining through tunnels to other voids through to other tunnels. This is the high density part. It's all in one piece. And here's the low density part. And there you can see this big void here, and you can see the tunnels leading through to the other voids. So this is sponge-like. This is a paper by Bond in 1995. They showed this computer simulation, his colleague, and there were colleagues here too. They showed a computer simulation done by Klippen. They studied something different. They studied the velocity flows in the initial conditions. And if you have a filament like this, connecting filament like this in the initial conditions, then there'll be velocity, it'll pull stuff toward it with velocity flows that are coming in from two directions here. If it was a pancake, it'd only be pulling things in from along one axis here. So they analyzed these velocity flows, and they were getting flows that were produced by filaments in the initial conditions, characteristically. And so this confirmed what we'd said all along, which was that the filaments are present in the initial conditions. They're part of the sponge-like nature of the initial random conditions. And of course, what happens is that after the filament is formed, then gravity continues to pull it together. So by late times, you're going to get, it's going to be narrower filaments connecting these clusters of galaxies. And so it looks like a web. They call this the cosmic web. This is the first paper to use that word. And that word has stuck to describe this structure. So this confirmed what we were saying earlier. Later, we've done the Sloan Digital Sky Survey, and Mario Urich and I found this large filament here, which we called the Sloan Great Wall, and we measured its length to be 1.37 billion light years. It was about twice the size of the Great Wall of Geller-and-Hukra. We were looking at a bigger volume of space. This got Mario Urich and myself into the Guinness Book of World Records. And we didn't even have to eat 80 hot dogs in 10 minutes. But let me speak up for this record, because there's a lot of largest things in the Guinness Book of World Records. There's the largest ball of twine. There's the largest building. But of all this is the largest structure in the universe. The previous record holder was the Great Wall of Geller-and-Hukra. Of all the largest things in that book, this is the largest of the largest. Okay, so anyway, we're continuing to find filaments. Let me go back to this picture. This is, I'm going to show you a close-up of this end of the Sloan Great Wall. And this is a picture made by my student, Lauren Hofstetter. And what he's done here is we've put the actual pictures of the galaxies from the survey at exactly the right locations, the right distances from the Earth in the picture. And you can see all these galaxies here in this rich eastern end. But they're 50 times enlarged, so you could see them. In other words, if the galaxies were this size, this picture should be 50 times larger, showing you the vast distances between these galaxies and the tremendous size of this Sloan Great Wall. Now, in about 2005, the Europeans, led by Sprengel, did a giant computer simulation of structure formation in this inflationary Big Bang model with cold dark matter. And they used 10 billion particles. This shows how computer simulations had gone since the time Park did his. And they found this wonderful picture of the sponge-like topology with all these filaments connecting the clusters of galaxies. This is a beautiful picture. Now, they also did slices of their survey to compare with various observational ones. So here's the two Sloan Great Wall and the Great Wall of Gellern-Hooker. They made a slice just like this in their observational set, and they found this Great Wall here, which is quite as long as the one that we're seeing here, and then one that looked quite like the closer one that we see of Gellern-Hooker. So these simulations were able to reproduce. As we've gotten bigger and bigger simulations, they've been actually better and better able to agree with the bigger and bigger observational samples that we're seeing, which indicates that maybe we're on the right track. Here's how these things have progressed. The first little cube I showed you was this tiny thing, and this is the Great Wall of Gellern-Hooker here in 1994, and then in 2006 we made, this is two large survey regions from the Sloan Digital Sky Survey. The Great Wall, the Sloan Great Wall is down here, and you can clearly see this is the high density half. This is a sponge-like structure. So every survey that we've done has shown a sponge-like structure of the high-density region. We invented a statistic called the genus here, which measures the number of holes minus the number of isolated regions in that density contour surface. And we were seeing about 50, 60, 70, about 80 holes in this sample. And the jagged line is the observations here. And the dashed line, which follows it so closely, is the 12 mock catalogs that we made from n-body simulation that used the exact random initial conditions and power spectrum of fluctuations you expected from inflation. And this fit perfectly, explained the number of holes. And these are at different density contours. Now, this is the median density contour, but these are higher and lower density contours. It fits at all the density contours. This is quite a spectacular affirmation of the inflationary predictions. This is the cosmic microwave background. It's an all-sky picture taken from the WMAP satellite. I brought a model of this. When we're at the center of this sphere, we're looking out in space. No matter which direction we look, we see the cosmic microwave background coming us from all directions in the sky, like from all over a big sphere. We're looking out in space and back in time. So we're seeing this as 13.8 billion years ago, just 380,000 years after the Big Bang. And that means that the radius here, the so-called look-back time distance out to this that we're seeing is 13.8 billion light years. And so this is the cosmic microwave background that we're seeing. And we're seeing fluctuations in this of 1 part in 100,000. And these are the fluctuations that are going to grow up to form this structure that we see. And here is a picture from Planck. This is a graph of the amount of power in this in different angular sizes. So a lot of those spots you see are like at 1 degree. And the red dots here are the experimental data from the Planck satellite. And the green line, the green band here, is the predictions of this standard now inflationary Big Bang model, and the agreement is just outstanding. And these peaks here represent acoustic waves in the early universe, and you can even look at the amplitudes of these and figure out the ratio of dark matter and normal matter and so forth. So this is a spectacular result. Now, I mentioned acoustic waves. If you take a place where there's going to be an extra lump of ordinary matter here to make, it's going to end up making a galaxy, that's like dropping it's like dropping a rock in a pond. The sound waves will go out here. They'll produce a ripple out here, and this freezes in when the atoms, when the electrons and protons recombine to form hydrogen. And so there's an extra normal matter here, and you expect this to give you a slight excess chance of finding galaxies at this distance from where you find your starting galaxy. So we can look. This is our telescope here for the Sloan Digital Sky Survey. Here's a picture of a typical galaxy that we're using here. So if you locate on a galaxy, you ask yourself the question, is there an extra little bump in the number of galaxies when you get to this special radius that you can calculate? And the answer is that Eisenstein found this extra bump in the data, and so this is a ruler that you can apply to the cosmic web. And the cosmic web expands every time the universe expands by a certain factor. The cosmic web stretches and expands by that factor. So you can use this as a ruler to tell you about the expansion history of the universe. Now, as I said, the accelerating expansion that we're observing today, which was discovered by supernova observations, we call this dark energy. And we can use this detailed measurement of the expansion history of the universe, which comes from supernova, comes from this Sloan Digital Sky Survey, from these measurements of this bump, and from the cosmic microwave background, and from gravitational lensing data. Thank you again to Zwicky. And you can put this all together. And a student of mine, Zach Slepian, found a nice fitting formula to fit this data. And we can measure then the ratio of the pressure to the energy density in this dark energy, which makes up about 70% of the stuff of the universe today. And we've got about 4% ordinary matter and like 26% dark matter. But we can measure actually the pressure and energy ratio by using Einstein's field equations. And so the best answer that we've gotten, combining all this data, these groups of people, teams of large number of people, using this fitting formula, the value we find is minus 1.008 plus or minus 0.068. So within the errors of the observation, this is equal to minus 1. Now, Einstein would be very pleased with this because he invented early on a term to add to his field equations called the cosmological constant. And this was in the hope of producing a static universe model. But then in 1934, Lemaitre found that if you moved this constant from one side of the equations to the other, it could represent a vacuum energy with a negative vacuum pressure. And so this is what we think we're looking at today. It's not a constant for all time, but it's something that can actually vary through the history of the universe as the physics changes. In the early universe, we expect that some of the forces were united and that therefore we had a high vacuum energy. We have a low vacuum energy today. So this looks like if this stays 1, the vacuum energy in the universe is going to stay constant. The universe is going to expand forever, doubling in size every 12.2 billion years. And eventually, there will be, we're talking more than 10 to 138 years from now, but maybe less than 10 to the 10 to the 34 years from now, long time in the future, eventually we expect to see bubbles of lower density vacuum occurring, like bubbles in an eternally fizzing champagne. So this is our view of the cosmic web today. This was taken in the infrared by the 2-mass survey. And this is an all-sky view again, like the cosmic microwave background picture I showed you. We're looking here toward the center of our galaxy. You can see it looks quite similar to Andromeda. We're in the plane of the galaxy, so we're looking at the center. This is in the foreground. And these dots here are all galaxies, and the colors are indicating how far away they are. And so you can see the filaments here connecting the clusters of great galaxies in this sponge-like pattern. And so you should realize when you look at this picture that you're seeing the fingerprint of inflation. You are seeing some of the largest things in the universe, but you're also seeing the oldest things in the universe, because these began as small vacuum fluctuations made in the first 10 to the minus 35 seconds of the universe. And by studying this cosmic web, we therefore can learn something about the very early universe. And also, by measuring it, we can find out something about the future dynamics of the universe over the next trillion years as well. Thank you.